Right. So any idea what you are going to learn about in this chapter? If any of you have come across laws of motion already. Okay, fine, not an issue. So till now, like if you look at all the chapters that we had discussed or gone through, first we talked about units, measurements, dimensions, how to report errors and all. Then motion in a straight line. Basically, we learnt about some simple physical quantities like position, displacement, velocity, acceleration, and some calculations based on that. We did those calculations for motion on a straight line. And the next chapter, we did those same calculations for motion in a plane, 2 dimensions. We learned a little bit about circular motion also. So in this chapter, laws of motion, we are going to introduce some more physical quantities. We're going to learn about some more physical quantities and some basics of how to describe what happens to a system. We'll be learning some basics of how to tell what happens to a system, how to predict, okay, the motion of a system. Fine. So tell me, any one of you, what is your idea of force? I'm sure you all must have come across this word force in daily life. So according to you, what is a force? Pawan, how would you describe force?
సార్ ఇప్పుడు ఒక ఆబ్జెక్ట్ కదులుతుందండి దానికి ఎంత కొంత ఫోర్స్ ఉంది.
So you are saying if an object is moving, it has some force. Okay. Yusuf, what is your idea of force?
So same as Pawan.
Fine. Saket, what about you?
Same, sir. If an object has a push or pull force,
If an object has
it's a force of push or it has pull, it is force.
push or pull, okay, okay. Fine. Aishwarya, what about you? What is your idea of a force? Okay, fine. We'll discuss. Now, some of you said if an object is moving, it has force. No, that is not correct. And it's like common misconception actually. You can't say an object has force. Force is not something which an object has. Force is something which one object exerts on another object. Okay. But let me just clarify what you all were thinking, like unknowingly. If an object is moving, it has something called momentum. Momentum is something which a system or an object can have, okay, that belongs to the object. Force is not something that belongs to the, you can't say an object has force in it. You can say an object has momentum, you can say an object has energy, okay, right. Now, this is the most common and most appropriate definition of force, I would say. Force is a push or a pull. This is correct. Okay. Now tell me examples of this. Use of you tell. Do you observe any pushes or pulls happening I mean, with you or with anything else in the surroundings during, like in your daily life?
Yes, sir.
Give some examples.
So
Examples.
pushing, I think pushing a table around.
Okay,
So-
pushing any object, literally pushing with your hands.
Yes, sir. And
Correct.
pull-ups, you could say as pull, sir.
Okay, you can pull yourself
Pull
up.
your body
You can
up,
push
yes.
something away from you. Correct. Okay. Pawan, you tell me examples of anything getting pushed or pulled by anything.
సార్ పుషింగ్ ఏ కార్ అండ్ pulling a pulley.
Pulling a pulley using what?
Thread.
Rope. Okay, yeah, you pull the rope. You don't say you are pulling the pulley. You say you are pulling the rope. Okay, fine, fine. See, whatever examples Yusuf and you have given till now, they all involve person literally pushing or pulling. Can any of you give me examples of objects pushing or pulling each other without the involvement of a person?
You're a magnet pulling iron bar.
Good, good. Magnet attracting another magnet or magnet attracting pieces of iron. Fine. Any other examples you all can come up with? Where else do we observe pushes and pulls in daily life?
Sir, electron.
Electron. Okay. Charges. Okay. Like charges repel, unlike charges attract. Correct. Those are also examples of pushes and pulls. Fine. So anywhere, if one object pushes or pulls or another object, we say they are exerting force on each other. Okay. And in fact, you don't have to dig your brain so much also. It happens all around us, pushes or pulls. Like you all might be having a laptop or at least a notebook in front of you right now resting on a table. Okay. Now we know that had the table not been there, okay, imagine this is the table surface and let's say there is a book placed on it. Fine. Had the table not been there, the book would have fallen down. So the table is kind of supporting it. Okay. So the table is exerting a force on the book. It's pushing the book in the upward direction. Otherwise, it would have fallen downward. You may be holding a pen in your hand. Okay. You will be pushing it, you will be pulling it, depending on what you want to write or draw. They are all around us. Fine. Okay. So force is basically a push or a pull on any object. Correct. And see the examples that you have given, some like Pawan said, electron. So the force is exerted by one electron on another electron. You don't say electron has force in it. Okay, no. Electron exerts force on another electron. That is correct. Okay. And first example also, someone said pushing a car. So when you push a car, you are exerting force on the car. So remember, force is always exerted by one object on another object. You can never say an object has force in it. That doesn't make sense. Okay. Again, from everyday experience itself, you all tell me, when you exert force on an object, whether it's a push or a pull, what do you see happening to that object? Like what kind of changes can you expect in the motion of the object?
A change in position.
Change in position. Okay. An object may go from one place to another place when you apply a force on it. Makes sense. Correct. What else? Change. I mean, position is one quantity that you have considered, and you said a force may change the position of an object. That's correct only. What else can a force do? What other quantities can it change or disturb from your everyday experience? Okay, suppose a bowler throws a ball and the batsman hits it. Batsman hits the ball means batsman exerts a force on the ball. What does that do to the ball? Just describe what happens to the ball due to that hit, due to that force. When a ball is hit by a bat, what happens to it? That's the question.
Sir, దానికి కొంచెం ఫోర్స్ వచ్చి కొంచెం డిస్టెన్స్ యాడ్ అవుతుంది.
On you are again saying it gets some force. Never say it gets some force. I mean, the question itself was, if we exert a force on the ball, what happens? You should not say if we exert a force, it gets force. Okay, don't say that. What was the next thing you said?
Sir, travel some distance.
Okay, travel some distance is like changing position only. Can you tell anything else? Like, see, we have learned some quantities till now, right? We know about position of an object. We know speed. We know velocity. We know acceleration. So we have learned some quantities till now. So tell me, when force is exerted on an object, which of these, or do any of these get disturbed or changed? That is my question.
Sir, velocity and angle with respect to ground.
Okay, velocity could change, direction could change, you are saying. Okay. When you exert force on an object, can its speed change or not? Is it possible or not? I'm not asking if it always happens, but can it happen?
Yes, sir.
It can. Okay. So basically, from everyday experience, like suppose there is a bottle resting on the table, you pick up the bottle. It was at rest. You disturbed its state of motion. You made it move. Fine. Suppose there is a ball which is already moving and a batsman hits it. Ball is already moving. It's in state of motion only. But when you hit it, you will be changing its state of motion. You will be changing the way it moves. Right? So basically what a force does is it tries to change the state of motion of an object. Like from our everyday experience, this is what we see forces doing. Okay, they change how an object is moving. Okay. Now I use the word tries to change. I didn't say it changes. That means there is a possibility that it does not change the state of motion also. There is a possibility that some forces do not change the state of motion of an object, or they fail to do it because of some other agents coming into play. So now one of you tell me an example of a situation where a force acts on an object, but nothing happens to it. Give me an example of a situation where a force acts on an object, but nothing happens to the object. Nothing changes about the object.
So pushing the wall.
Good. Okay. You push a wall. Okay. If it's properly built, if it's strong enough, most likely nothing will happen to it. Okay. Fine. Any other examples?
Sir, an asteroid undergoing air resistance.
Asteroid?
Undergoing air resistance, like it is coming down on Earth.
Okay. Asteroid falling to the earth and experiencing air resistance along the way. Is that what you said?
It does not have any change. Yes, sir.
See, in case of asteroid, you can't say nothing happens to it. Asteroids or anything actually, even spacecraft, like failed spacecraft, when they fall back to the earth, as they pass through the layers of atmosphere, as they brush against air molecules or gas molecules along the way, a lot of heat gets generated. In many cases, space debris will be there, no? Like failed spacecraft and all, they tend to fall back to the earth. In many cases, as they enter into the Earth's atmosphere, before they reach the ground, before they reach the surface of the Earth, in the atmosphere itself, they'll get burnt. Okay, air resistance is a significant force at that scale. At such high speeds, air resistance generates a lot of heat. Okay, so you can't say it doesn't do anything. It slows them down also. Okay, in case of asteroid also, they get heated a lot once they enter into the atmosphere, and a little bit of slowing down will happen. We may not be able to appreciate it, or it may not slow down significantly that it becomes harmless. Okay, but some change will be there. Any other examples of forces acting but not causing any change to the state of motion of an object? Okay, fine. See, there are many examples like that same table and book example you can take. Book resting on a table. Table is exerting a force on the book, but is anything happening to the book? No, it stays where it is. Okay, is anything about the book changing? No. Fine. Or let's say there is one book on the table and you put another book on top of it. Will anything happen to the first one? Okay, it may get a little bit compressed. After that, force keeps acting. Okay, the first book, like you can take two books, one placed on top of another. You imagine it like this. 2 blocks or 2 books. So when you place B on top of A, little A may get compressed a little bit, but once that is done, B will still be exerting a force on A, but after that nothing happens to A. Okay, so I just want you to understand that there is a force acting on an object doesn't mean something will definitely happen to that object. Okay, force is something which tries to change the state of motion of an object, but it may not always be successful. It depends on other factors as well. We'll discuss what those other factors are. Okay. Can any of you tell me, like, what are the common forces that we come across in daily life? What are the common kinds of pushes and pulls that we experience or objects experience in daily life?
Sir,
Gravitational
gravitational and
force.
frictional.
Okay, gravitation, first one. Now, see, the gravitational force that we or any object on Earth experiences is what we call as weight of the object. Fine. How strongly an object is attracted by the Earth is what we call as its weight. So weight is basically a force. Fine. Tell me, in which direction does the Earth attract any object?
So towards its center.
Towards the center of the Earth. Correct. It's actually towards the center of the Earth. If you imagine, Earth is roughly spherical, not exactly, but roughly spherical in shape. So imagine this as the Earth. Imagine an object somewhere here. Earth exerts a force on that object, which is directed towards the center of the Earth. But if you zoom into this, okay, it appears like for the size of objects that we come across in daily life, the Earth size is very large. Okay, so for us, it appears to be almost flat. And let's say this is the object. If you say a force is acting this way, okay, center of the Earth is very far from us. From the surface of the Earth to the center is 6,400 kilometers. So you can just say that the gravitational pull of the Earth is vertically downward. Okay, it's actually towards the center of the Earth. That is correct, but you can simply say it is vertically downward. Okay, towards the ground, right? And yeah, you all generally said gravitational force. That's one of the forces. But I said, what are the forces we experience in daily life? Now, the most significant gravitational force we experience in daily life is that of the Earth. Okay. See, every particle, okay, particle means you can say small dust particle, or you can call a molecule as a particle, you can call an atom as a particle, you can call an electron also as a particle. Every particle exerts gravitational force on every other particle. Okay, you will be exerting gravitational force on the screen in front of you. The screen in front of you will also be exerting a gravitational force on you. But do you really feel it? Do you feel any significant pull towards it? No. Okay, but Earth's gravity we all feel. Fine. So for now, we are only going to consider the gravitational force of the Earth, which is what we call as weight. Okay, and it's a force. Force is a vector quantity, and it is directed. Weight of any object is directed vertically downward. Okay. If any of you can, you tell me, is there any object which does not have any weight?
So a feather.
Do feathers not fall to the ground? Yes or no?
Yes, sir, the fall down, sir.
That means they do experience, like, it's the Earth's gravity which pulls them down, right? So they do have some weight.
Light, sir.
Light, good, very good example. But I can say light is not something we can discuss at this level. I would say research is still going on. Light, you can consider it as a stream of particles. You can consider it as a wave. Light has something called dual nature. You learn about it in 12th class. And you can't say light does not have weight. Have you heard of a black hole, Vanilla?
Can you repeat it, sir?
Have you heard of a black hole?
Yes, sir.
What do you think they are? What happens due to black holes? Or anything you know about, what do you know about them?
They are in space, sir.
Correct. They are in space. What else? Why are they called black
Sir, they
holes?
form when stars collapse into themselves.
Okay, a black hole forms when a star collapses into itself. Reasonable. Yeah, correct. Why is it called a black hole?
It is black.
Correct. Fine. Now this is an open question to all of you. Most of you might be in rooms which have white light. Some of you may be in rooms which have yellow light. Okay. But I'm sure you must be seeing some black objects around you. Even though there is light falling on an object, why does the object appear black? So my question is, why do black objects appear black? Is black a color? I mean, in everyday usage, yes, black is a color, but scientifically, is black a color?
Sir, black color has higher tendency to absorb light.
Okay. Okay. See, scientifically, black is not a color. Black is basically the absence of all colors. Absence of any visible color. Our brain shows it as black to us. See, you all must be knowing the basics of vision. Now, how do we see things? Light falls on an object, or the object emits its own light. Then that light has to enter into our eye. Then we can see things. If no light comes from an object into our eye, okay, for example, this pen, it appears black to me. Okay. What is happening here is, see, in my room, there is white light. It is falling on this pen. But from the pen, none of that white light is getting reflected back into my eye. That is why it appears black. Okay. So when you get no color from any object, that object looks black to us. So basically, black is the absence of light. Okay. In a particular, I mean, from that object towards you. There's no light coming from that object towards you. Then it appears black. Now, we were talking about black hole. What happens in black? Why they are called black holes? You said they are black. That is correct only. If they are black, it means when light goes towards it, it cannot come out of it. Okay. There is no light which comes out of a black hole, even if you send it from the other side. So basically what we were discussing is there anything which does not experience weight, or is there anything which is weightless? That was the original question. And one answer to that was light. Now you can't say light does not have weight, because I see this is not properly researched yet. It's still going on, but there is a theory that black holes attract light through gravitation. Fine. And their gravity is so strong that even light gets trapped. Okay. So in that case, light has weight and it falls into the black hole. Okay. On Earth, what you said may be reasonable. On Earth, you can say light is weightless. Earth does not cause any significant deviations to how light travels. Okay. Okay. Good example. Good example. Good discussion we had. Any other objects you think are weightless? Anyone? Okay, right. So see, we are just learning the basics of mechanics, and the objects that we are going to consider are everyday objects like blocks, strings, general objects, okay? Cars, person and all. So they will be having weight, significant weight will be there. We will consider the weight of these objects. Weight is something which is directed downwards. And can any of you tell me how the weight of an object is calculated? What is the formula for weight of an object? You all must have learnt in lower
Force
classes. No?
that
What did you say?
force that is exerted on a person towards the earth.
That is the definition of weight. Okay, yeah, we discussed that. Not just a person. The force exerted by Earth on any object, the gravitational force exerted by Earth on any object is called the weight of that object. How is it calculated? How do we say how much is that weight? Okay, I'm sure you all must have studied this in your lower classes. W is equal to mg, where m is the mass of the object. G is simply acceleration due to gravity. Do any of you remember this formula? W is equal to mg. You never came across this in your lower classes? I'm
Yes,
sure it
sir.
is there in 10th. Okay, anyway, this is how weight of an object is calculated, okay? Mass multiplied with the acceleration due to gravity. Okay, now I will ask some uncomfortable questions. Tell me, what is the unit of mass? SI unit of mass, anyone?
kg, sir.
Kg. Acceleration due to gravity,
Meter per second, sir.
meter per second square. So what should be the SI unit of weight?
kg meter per second.
So weight must be in kg meters per second square. Okay, correct. This is the SI unit of weight. Okay, what you said is correct only. Pawan, how much is your weight?
54
54 what? Chocolates or biscuits? Tell the unit.
kg, sir.
54 kg. Okay. Listen, all of you. I asked him his weight and he said 54 kg. And from the little bit of physics that we have studied, we know kg is the unit of mass. But he said this is his weight. We all tell like this. Is this correct? So what exactly is 54 kg? Suppose a person says their weight is 54 kg. What do they mean by that? Do they mean their weight is actually 54 kg meters per second square? Or do they mean their mass is 54 kg? What is the meaning of this? Just if you know anything, you tell what you know, or you tell what you think. Or is it something else?
Sir, mass is 54 kg.
Okay, so Pawan is saying maybe they mean their mass is 54 kg. Okay, so when we ask people about their weight, they tell us their mass. So if you know physics, you calculate my weight. You know, I don't want to tell my weight. Okay, fine. Let it be. What do the others think? Saket, what do you say? If a person says their weight is 54 kg, what do you think they're meaning by that? Someone said something, but I could not, I mean, it was not clear. Okay, anyway, let us understand this. Fine. Now see, weight. is calculated as mass multiplied with acceleration due to gravity. So the SI unit is supposed to be kg meter per second square. In fact, that is the SI unit of force also. Okay, weight is a force itself. So force, the SI unit is kg meter per second square. But since Newton did a lot of research on forces, they named this unit after Newton. So this itself is called 1 Newton, denoted by the symbol capital N. Okay, and I think I told you this in units and measurements. When a unit is named after a scientist, I mean, even if a unit is named after a scientist, if you are expressing the unit, it has to be written in small letters only. Okay, like one of you tell me, what is the SI unit of current?
Ampere, sir.
Ampere. Okay, so suppose you want to say something like 2 amperes, you can write 2A, or you should write 2 small amperes. Okay, even though the unit is named after a scientist, the unit should never be written with the full unit should never be written with a capital letter. Okay, it's a rule. Okay, so Newton is the SI unit of force. Newton means 1 Newton means 1 kg meter per second square. 2 newtons is 2 kg meter per second square, and so on. Now, weight of an object is to be expressed as mg. It should be expressed as kg meters per second square. But we have this habit of expressing it in kg. Understand what that means. Okay. Newton is the SI unit of force, but there are other units of force as well. Now see, suppose there is a mass of 1 kg. Consider an object whose mass is 1 kg. We know the formula for weight is mg. Mass is 1 kg here. Acceleration due to gravity, let's take it as 10 meter per second square. Then the weight of that 1 kg object becomes 10 kg meters per second square. You write it as 10 newtons. Now, whose weight is 10 newtons? Which object's weight is 10 newtons? Okay.
1 kg block.
An object whose mass is 1 kg, that object's weight is 10 Newton. Okay. So we can say that 10 newtons is equal to the weight of 1 kg mass. Fine. You can also say it, you can also call it as 1 kg weight, kgwt. You should read it as kg weight. You can also call it as 1 kg force, kgf. Kg weight and kg force are the same thing. And 1 kg weight means 10 newtons. That's the weight of 1 kg. Okay. Newton is the SI unit of force. Kg weight is also a unit of force. Kg force is also a unit of force. So these are other units of forces. Fine. Now, let's come to that point, weight of a person or weight of an object. Usually in daily life, we tend to express weight in kgs. But actually, when a person says, or when a weighing machine shows the weight of a person as 54 kg, it means the weight is actually equal to 54 kg weight. And each kg weight is 10 Newton, no? So that person's weight is actually 540 newtons. Okay. So we have this habit of expressing weight in kgs, but that is actually the unit kg weight. It's not kg, it's kg weight. We just say kg, but it means kg weight. Okay. So when the object, when like you go to buy onions, let's say you buy 3 kg of onion, you are actually buying 3 kg weight of onion. Okay. And what Pawan said is also correct. When a person says their weight is 54 kg, it actually means their weight is 540 Newton. And you equate this to mass into acceleration due to gravity. It means their mass is 54 kg. That is also correct. Okay. Actual meaning when the weight of an object is expressed in kgs is that the unit is kg weight, but it also means that the mass is that much. Okay. So remember this, all of you. Kg weight, the name itself says kg weight, the weight of 1 kg. So weight of 1 kg is how much? 1 kg into 10 newtons. So 1 kg weight is equal to 10 newtons, or 1 kg force is equal to 10 newtons, assuming g is 10 meters per second square. If g is only 9 point, it's taken as 9.8 meter per second square, then you will equate it to 9.8 newtons. Okay, so kgf or kg weight is a bigger unit than Newton. It is almost 10 times of a Newton. Okay, so remember these things. Weight is the gravitational force on any object exerted by the earth. It acts in the vertically downward direction, and it's calculated as W is equal to mg. And it's one of the very common forces that we come across in daily life. Okay, and when I asked you, like, you almost could not think of any object which does not have a weight. Okay, right. Can you tell me any other forces, means any other pushes or pulls that we come across in daily life? Can you think of anything other than gravity?
Sir, electrostatic and electromagnetic forces.
Electromagnetic includes electrostatic. Okay, they are not separate. So you are saying electromagnetic forces. Fine. Where do you see them in daily life?
Sir, in iron, sir.
Iron and, like, how do you see that?
Sir, basically it has electromagnetic force because inside it is powered by magnets in many of them at least. So,
Okay, so you are talking about magnetic force and you are calling it electromagnetic. Correct. Okay, yeah, it's a force that is quite common, but not as common as gravity. I mean, your example is valid only. We see them in daily life, yeah, but not so frequently. Or do you say you see it all the time? Saket?
no, sir.
Okay. So in your 12th class, you have a separate chapter. You have, like, your entire 12th class is dedicated to study of electromagnetic forces and their effects. So what you said is correct only, but we'll not be considering that now. Any other pushes and pulls that we come across in daily life?
Sir, frictional force.
Friction. Okay. See, friction is also electromagnetic in nature. Okay, if you study friction in depth, how it is happening and all, the reasons are charges. The reason is charge. Okay, but we'll not call it electromagnetic force. The way we see it, it appears to us as friction. Okay? So we'll consider that as one of the common forces that we come across in daily life. Correct. We'll be studying that in this chapter. But a little later, not right now. But yes, friction is a very common force that we see. It's almost everywhere around us. Next, any other pushes or pulls that we come across in daily life? Okay, first of all, tell me some cases where you observe friction acting.
Sir, when a man is going forward.
Okay, when a person is walking forward. Okay, so while walking, there should be friction acting, or friction is needed to walk. Correct, reasonable. Any other examples? So you experience friction only while walking, nowhere else. How are you holding the pen? Do you think friction is needed to hold the pen or not?
Yes, sir.
Huh? Do you think friction is required to hold anything or not? A pen, tumbler, bottle, whatever it is, you need friction, right? How does a vehicle come to rest? Is friction needed there or not?
Yes, sir, it's needed, sir.
Okay. How does a vehicle gain speed? Is friction needed to gain speed or not? Pawan, what do you think?
Yes, sir.
Needed. So friction can help us in gaining speed also.
Yes, sir.
Okay. Fine. That is correct. It can. We'll discuss all those in detail in this chapter itself. So yeah, friction is one of the very common forces that we come across. But there are some other things we need to know before we talk about friction. Okay, so we'll come to that a little later. Next, any other common forces we come across in daily life other than gravity, friction, magnetic force?
For nuclear forces,
Hi, Babu. You don't experience nuclear forces in daily life. No. They are very rare.
sir,
I mean, they are
atoms are
there.
bounded by, I mean,
Correct,
nuclear.
correct. They are there, but you don't see their effect. No. Like you don't see things happening around you because of nuclear force. No.
Air resistance, sir.
Air resistance comes under friction itself. Basically, it is fluid friction. Okay, liquids and gases, they are called fluids. Correct. It's an everyday force that we experience, right? Okay, you told about gravity, that is the weight, gravitational pull of the earth. You told about friction. Okay. Now, when I asked you some examples of pushes or pulls, you said person pushing a car. When a person pushes a car, what is the name you give to that force? Any idea? Is it one of these? Is it gravity? Is it friction? Or is it something else? What do you think?
Sir, contact force,
Contact force. Is it different from gravity and friction or not?
sir, it's different from gravity, sir.
But not much from friction. Okay. Okay, when a bat hits a ball, is it gravitational force? Is it friction? Or is it something else?
So it's just force, sir.
Okay, it's just a push, you should say. Yeah, we call that as normal force. Okay. Someone said contact force. That is also correct. Both friction and normal force are contact forces. They require contact between two surfaces. How are they different from each other? Let us see. Do any of you know the meaning of this word normal? Normal doesn't mean usual. There's a different meaning here. Do you know the meaning, anyone?
So 90 degrees.
Perpendicular. Correct. Normal means perpendicular in this case. So how are friction and normal force different? Let us see. Suppose again, let's say this is a surface and there's an object resting on it. Or let's say this object is being dragged on the surface to the right. So you imagine an object or a block or a bag, something being pulled on the floor. Obviously, there is one force pulling it. Let it be there. Let us give it the recognition that it deserves. What other forces do you think act on the block? Anyone? Will there be any other forces acting on the block as it is being dragged on the floor?
Sir, downwards only.
Its weight will be acting. Okay. Earth will be attracting it in the downward direction. Correct. So one of the forces acting on it will be its weight. That is mg. You can calculate it as mg. Correct. Any other forces do you think the block experiences when you drag it on the floor?
Friction, sir.
Friction. Correct. Now, what exerts friction on the block?
So the ground and the block.
The ground exerts on the block. Correct. Yusuf, can you tell, like in this case, if the block is being dragged to the right, in which direction does friction act?
So left.
To the left. Correct. So friction is one of the forces and it acts, we show it to be acting like this. Because like from your daily experience also, you just slide your palm against a surface, you can feel friction acting on your palm. Suppose you are sliding your palm to the right, friction acts to the left, and it acts where your palm touches the surface, not somewhere else. Okay. So this block's lower surface is touching the floor. So the floor exerts friction on the lower surface of the block and it exerts to the left. So we'll indicate friction like this. Correct. Any other forces you think will be acting on the block?
Sir, normal force.
Huh. What exerts normal force on the block? See, normal force is something we just discussed. As the name suggests, it is perpendicular. Now, someone said it's just a push, and I told the name is normal force. So I'm asking you, what push or what is pushing the block? What is exerting normal force on the block?
Sir, surface.
Surface, correct. Earth is trying to pull the block down. It's trying to make it fall down, but the surface is supporting it by exerting a normal force this way. Okay. Now we'll talk about why it's called normal force. You see, there are two surfaces in contact here. The lower surface of the block and the ground. They are in contact here. Okay. So we call them as surfaces in contact. Now, weight, which is the gravitational pull of the earth, it does not require contact. Okay. Gravitational force is a non-contact force. They are also called, there are other non-contact forces also. They are called forces acting at a distance. Okay, non-contact forces simply. Now, friction and normal force, they both arise when there is contact between the surfaces. See that general push that we talked about, it requires the contact between two objects. Fine, mechanical, it's a mechanical force. It requires contact between objects. So friction, normal force, they both require contact. That's why they're called contact forces. Now, if you observe normal force, as the name suggests, it acts perpendicular to the surfaces in contact, both of them. It acts perpendicular to the base of the block. It even acts perpendicular to the floor. Okay. Since it is acting perpendicular, it's called normal force. That's why it is given the name normal. Fine. So the general mechanical pushes that we come across in daily life, the technical name, the scientific name for that is normal force. Some call it as normal reaction force also. That's fine. Let us not use the term reaction for now. Let's just call it normal force. Okay. So when a person pushes another person, when a ball goes and collides with something, okay, against the wall or something, when a bat hits a ball, all those general mechanical pushes, they are all called normal forces. Okay. And why are they called normal forces? Because that force is perpendicular to the surface of contact. So let me write this completely, perpendicular to surface of contact. Fine. Now observe friction. Friction is acting to the left. Now the surface here is horizontal. Block surface is horizontal. Ground is also horizontal. Friction is acting to the left. Means it is parallel to the surface. So friction is also a contact force and it acts parallel to the surface of contact. There are no exceptions to this. Whether you are walking, driving a vehicle, holding a pen, whatever it is, if friction ever acts anywhere, if friction ever acts on any surface, it acts parallel to that surface. Okay. The perpendicular force is called normal. These two together, okay, friction plus normal together are called the net contact force between two surfaces. Okay. So we can define something called net contact force between surfaces. It is the resultant of friction and normal force. Okay, they are together called as total contact force. Okay, good. Friction, as I said, we'll discuss a little later. Normal force between two surfaces. Can any of you tell me on what factors it depends? Like weight depends on mass of an object. Object has less mass, it will have less weight. More mass, more weight. We experience that in daily life. And of course, it depends on acceleration due to gravity. So weight is m into g. Depends on mass, depends on acceleration due to gravity. Can any of you tell me the factors on which normal force depends? Okay, you take this example itself. Book resting on a table or a block resting on a table. Suppose this is the table surface and a block rests on it. We know there is some pushing between them. The block pushes the surface also pushes the block. Okay, it's like it supports the block. There is a force acting on it. On what factors does that force depend is my question.
Sir, mass and acceleration due to gravity.
So you are effectively saying it depends on the weight. Is that what you're saying?
Yes, sir.
Okay. So yeah, in this case, it may seem like the normal force, how hard the block presses on the surface, depends on its weight. Okay. Yes. In this case, it is true. Normal force depends on weight of the block, but I'll have to write in this case. Okay. But consider person pushing a car or a bat hitting a ball. They are also examples of normal force. How much force a person exerts on a car, does it depend on the person's weight? You may just tap the car, you may hit it hard, you may push it. It depends on, no, it does not depend on your weight. It may depend on your mood, but not weight, right? So tell me, does normal force always depend on weight? That is my question now. The mechanical pushing force between two objects, does it always depend on weight of the objects? Yes or no? Okay, in this case itself, let us consider. Let's say this block has a mass of 10 kg. It will be exerting significant force on the surface. Okay, this is the horizontal surface on which the block is resting. It will exert some force on it. Fine. Suppose you pull this block up by a small amount of force. Let's say some 4 Newton force you apply. You gently, you just try to lift it up. You're not actually lifting it up, but you're trying to do it. Can one of you comment on what happens to the normal force here? Will the block still be pushing on the surface? Will still be pressing the surface with the same force, or lesser force, or greater force than before? Aishwarya, what do you think?
Sir, with lesser force.
With lesser force. We can experience that in daily life also. You keep any object on your hand, okay, on your palm, you can feel that the object will be exerting some force on your palm. But if you support the object, if you try to lift the object using some other agent, here it will feel lighter. Okay, the force exerted here will reduce. Now, what force is the bottle exerting on my palm? Normal force. Okay, it is pressing my palm in the downward direction. My palm is pushing it up. Okay. Now, when I try to lift this bottle up with my other hand, the force with which the bottle presses my palm is decreasing. The normal force is decreasing. Okay. So normal force depends on weight. It may depend on weight in some cases, but that's not the only thing on which it depends. Normal force depends on other interactions that the object has with the surroundings. Fine. So as a result, there is no fixed formula for normal force like how we have for weight. Weight, the formula is mg. You can calculate weight of any object. But you can't directly tell. I mean, there's no direct formula for normal force between two surfaces. It depends on what is happening to the system. Fine. Now see this same bottle on my palm example. If an external agent, if I add some more weight on top of this bottle, then how the bottle presses my palm will change due to that also. Normal force can increase also. It depends on how what other interactions the system is having, what other forces are acting on the system. Okay. So remember, there's never a direct formula for normal force. You should consider the other forces acting on the system, then you can tell how much the normal force is. But how to tell how much normal force acts between two surfaces? Listen. Now in this case itself, tell me, let's forget that 4 Newton force, 10 kg block kept on the ground. You all said, like you all know that the ground exerts some force on the 10 kg block like this. One of you tell me, the force exerted by the ground on the block, what is it resulting in? Or how is it helping? What is it doing basically? Or what happens if that force is not there?
Sir, force वाला block stationary level.
Okay, you are saying the force holds the block at that stage, at that level. It doesn't allow it to fall down is what you are saying. Correct. Okay. Now, you all might have used elevators at some point. Okay, lift, elevator, escalator also you can say. Any of those examples. Now you stand in the lift. Let's say you got into the lift on the ground floor and you press floor number 2. The lift takes you up. Okay. Now you are standing on the floor of the lift. So imagine a person standing on the floor of the lift. Tell me, what force does the lift exert on the person? What force does the force of the, what force does the floor of the elevator exert on the
Normal
person?
force.
Normal force. Okay. It's in the upward direction. On the person's feet, it will be acting. Okay. Now that normal force exerted by the elevator's floor is not just keeping the person at that level. Okay. Maybe the person got into the lift here on the ground floor. Now, lift can take the person up, right? So the normal force can even push an object forward, upward. Okay, it can make an object go up. It can make an object come down also. Okay. So the job of normal force is not to always keep something stationary. But in all these cases, whether the object is absolutely at rest, or the object is being pushed up or being brought down, slowly lowered down. That is also possible. Like, see, I'll keep this bottle on my palm. My palm is exerting a normal force on the bottle. In the upward direction, I'm exerting a force. But still, when I exert sufficient force, the bottle stays there. When I don't exert sufficient force, the bottle can go down also. I am still exerting upward force only. I'm exerting upward force, but I'm not giving sufficient amount of force. I'm allowing gravity to dominate. Then the bottle can be lowered. So my normal force is acting upward, but the bottle is going downward. That is also possible. Okay. It all depends on how much normal force is acting. But there is one thing common in all these cases, whether the object is just being supported, taken up, or it is being lowered, or it is being pushed to the sides, whatever it is, there is one thing common. The normal force will only be sufficient to make these surfaces move together. Okay. The force, the normal force, only prevents one surface from going into another surface. We are talking about solid surfaces here. So normal force prevents one solid from going into another solid, one solid surface from going into another solid surface. To do that, okay, to achieve that, how much ever force is needed, that much normal force will act between two surfaces. Like in this case, let's say the block is simply at rest, okay, on a horizontal surface. We know that the block experiences weight. Gravity is trying to pull the block down. Weight is calculated as mg, 10 into 10, its weight is 100 newtons. Okay, you can write it as 10 kg weight. Mass is 10 kg, weight will be 10 kg weight. Now, what is the normal force they're doing? See, it should not allow the 10 kg block surface to get into the floor. To prevent that, how much normal force is needed? 10 Newton normal force is needed. It has to, not 10 Newton, sorry, 100 Newton is needed. It has to counter that force. So we can say that in this case, normal force is 100 Newton. But that's not always the case. Fine. You'll see as we solve problems, you'll understand. So remember, normal force only prevents one surface from going into another surface. So basically, it makes the surfaces stay together. For that, how much ever force is needed, that much normal force will act. As long as they are in contact, they should have a common speed, common acceleration. Right. So friction and normal force are some very common forces that we come across in daily life. Both are contact forces only. Friction is a force, contact force, which acts parallel to the surfaces of contact. Normal is a force which acts perpendicular to the surfaces of contact. Fine. Another common force we come across in daily life is called tension. Do any of you know what tension means as a force? Manila, what is your idea of tension? No response. Anyone? What is your idea of tension?
Sir, okay, string active force.
Okay, a string, a force acting in a string. Fine. See, you don't have to consider a string also. Listen, tension basically is electrostatic in nature. Friction, normal force, tension, these are all not electrostatic, electromagnetic in nature. They all happen due to charges within a system. That's fine. But see, consider a solid object. For example, this pen. Okay. I don't know how many of you are able to see, but there's a red line here. Okay. Now, if I pull this pen outwards, okay, I'm pulling it, but nothing is happening to it. Okay, I'm pulling it outward like that. I want to rip it apart, but nothing is happening to it. Fine. So effectively what is happening, you call this side of the pen as A and this side of the pen as B. There is a bond between A and B. In fact, there are bonds everywhere. Okay, chemical bonds. You all must be knowing, no? That is what holds the object together. So what happens when I try to pull it apart like this? I am trying to break those bonds, but those bonds are not getting broken. They are attracting each other. I mean, this side of the pen is attracting this side of the pen. They are holding together. Okay, that holding force is what we call tension. When two objects in contact, they have a tendency to separate, but they are holding themselves back. That force is what we call as tension. Usually tension is seen when you try to stretch an object, whether it's a string or a rod, it could be a block, it could be anything. You try to stretch the object will not stretch. We in this chapter we only deal with solid objects, okay? Perfect solids. So when you try to stretch the object, but the object does not stretch, there is tension inside it, which is preventing it from getting stretched. So you can say tension is a restoring force. What does it restore? It restores the shape of the object. It keeps the shape intact. Tension is a restoring force that acts within an object when it is being stretched. Fine. Now you all come forward with examples. Where do you see tension acting? Someone said in a string. That is correct. Okay. Suppose, okay, let's write the definition first. It's the restoring force. What does it restore? It restores the shape of the object. It keeps the shape intact. Restoring force that acts within an object when it is stretched. Okay, that force is what we call tension. So one of you said string, tension acts in a string. That is correct. For example, suppose there is a roof or a ceiling and you suspend an object from that ceiling. Okay, like a pendulum you consider. Assume a ball is hung like this. So basically what is happening, the ball which is at the bottom of the string is pulling the string downwards. So the string has a tendency to get stretched. But does it freely stretch? No, because there are internal forces maintaining its shape. There are restoring forces within the string. That is what you call as tension. So basically what happens due to tension is tension pulls. Tension is a pulling force. Normal force is a pushing force. Tension is a pulling force. That's the basic difference between them. Okay. So here what is pulling what? The ball is pulling the string. The string is pulling the ball upward. Okay. Gravity is trying to make the ball fall down, but the string is pulling it up. Okay. So yes, there is tension in the string. So we say that the string exerts tension on the ball like this. Tension on the ball by the string. Okay. Can you give me any other examples of tension acting anywhere? Basically pulling forces. Think of pulling forces acting, situations where pulling forces are acting.
So tug of war, where two people are pulling a rope, opposite directions.
Okay, correct. Tug of war, two teams pulling on a rope. So pulling is involved, there is tension in that rope. Tension gets generated in the rope. Correct. Any other examples?
So a lift going up and down, like a lift, the cables in the lift.
Okay, the cables connected to a lift, they must be exerting tension to move the lift up and down. Correct. Okay. See, all these involve ropes and strings. Can you talk about tension in objects other than ropes? Anyone? Or tell me this, can a rod exert tension? Can tension develop inside a rod? That is my question.
Yes, sir.
Tension, as I wrote here, is a restoring force that acts within an object when it is stretched. Okay. So when you try to stretch a rod, will the rod try to maintain its shape or not? It will. There will be a restoring force. There will be forces between molecules holding them together. So tension will get developed. Okay, yes. So rods can exert tension. Next, can a water bottle exert tension or not?
Yes, sir.
Yes. Okay. Any object which has even the smallest of attraction between its molecules can exert tension. If molecules want to stay together, then there will be tension between them. Like when you try to pull them apart, they will attract each other. That itself is tension. Okay. So yes, any object can exert tension if there is attraction between its molecules. Right. So for now, these are the forces that we are going to be talking about. We will describe what happens to systems under the influence of these forces. What are the four forces we are going to consider? Gravitational force, normal force, tension, and friction. Okay. And see, just like normal force has no definite formula, tension also does not have a definite formula. Like see this pen, as I said, if I try to pull it in, rip it into two pieces, there will be tension developed inside it. There will be a restoring force developed inside it. Now, if I pull on it gently, the restoring force will also be gentle. If I pull on it hard, the restoring force will also be hard. So it's a force which depends on the other factors. Okay, it depends on the other forces acting on the system. So there is no definite formula for tension also. So if you ever want to find out how much tension acts anywhere, you will have to look at the system as a whole. You will have to see what other forces are acting on the system, what is happening to it. Based on that, you will answer. Okay, you will learn in this chapter. Fine. So what have we discussed so far? We discussed that forces are basically pushes or pulls that we come across in daily life. Okay. Any kind of push or pull, you can call it as a force. Now, there are different types of pushes and pulls that we come across. There are four fundamental forces in nature: gravitational, electromagnetic, and then nuclear forces. In nuclear, there are two types, strong and weak. Okay, these are the fundamental forces. How we see them in daily life is gravitational force, we experience it as weight. Okay, as I said, there is gravitational force between any pair of objects, between you and your screen, you and the water bottle, whatever it is, there is gravitational force, but you don't feel it. Which is the gravitation that you feel? That of the earth. Okay, so that we will consider in this chapter. Electromagnetic forces, these are forces arising due to charge within a system, or between two systems. Now, how do we see them in daily life? We see them in the form of tension, normal force, friction. Okay, someone said magnet attracting iron particles, or inside iron itself there is magnetic force. Yes, those are also there, but those we'll discuss in 12th class, not now. Some common ways in which we come across electromagnetic forces are in the form of friction, normal force, and tension. Those we'll be talking about. Nuclear force will not discuss as of now. Okay, nuclear force acts inside the nucleus of an atom. Outside, they don't show any effect. Okay, so as of now, it is, we'll ignore it. You learn about it in 12th class. Okay. And what does a force do to a system? It tries to change the state of motion of an object, and the reverse is also true. If the state of motion of an object is changing, there must be one or more forces involved. That is an important idea, because you will be given a system and asked some questions about the system. You have to visualize how the system is moving, what is happening to the system, and you should be able to explain which force is making that happen to the system. So whenever anything happens to a system, any change happens in a system, in the way it is moving, there must be one or more forces involved. Okay. For example, tell me, we know moon revolves around the earth. Revolving means going in circle. Going in circle means velocity must change. What force is responsible for making the moon revolve around the earth? Anyone? What force helps?
Gravitational force.
Gravitational force exerted by the earth. Correct. So whenever there is change in state of motion happening, there must be forces involved. Right. Next, suppose you exert some force on an object, or you exert equal force on different objects. Will they all move in the same manner? From your everyday experience, you tell me. Suppose there is a small stone and there is a big rock. Both are at rest on the ground. You apply the same force on both of them. Will the same change in state of motion happen to them?
No, sir.
No, right? One has a greater tendency to change its state of motion. Means for one object, it's easy to change the state of motion. For another object, it is difficult. Fine. This is something called as inertia of a system. Can one of you define inertia? Okay. Basically, it's the resistance. Okay. To the change in state of motion of a system. Some systems are ready to undergo change in state of motion. Some systems are reluctant to undergo change in state of motion. For example, let's call these objects as A and B. It's easy to change A state of motion. So we say that A has less inertia. It's difficult to change the big rock state of motion. If it is at rest, it's difficult to make it move. If it's already moving, let's say there is a rock rolling down a mountain, it's difficult to stop it compared to small stones rolling down the mountain. Okay, so we say that this has more inertia. It is more reluctant, or it has more resistance to a change in its state of motion. Okay, now tell me fundamentally what is the difference between the small rock and the big rock, small stone and the big rock? Anyone? What is the basic difference between them?
Sir, mass.
Mass, correct. So can we say mass is a measure of inertia? Greater the mass, greater the inertia?
Yes, sir.
Yes, sir.
We can. Okay, that is correct. Less mass, less inertia, and more mass means more inertia. But there is a condition here. We can say that mass is a measure of inertia of rest. Means how difficult it is to make an object start moving depends on its mass. Fine. That is what we call as inertia of rest. There's something called inertia of motion as well. What is inertia of motion? If an object is already moving, how difficult it is to change that object's state of motion. That is called inertia of motion. Okay. For rest, it is definitely, inertia is definitely measured in terms of mass. Okay. More mass, more inertia, less mass, less inertia. Okay. Can any of you tell me, or okay, I'm telling you mass is a measure of inertia of rest, but I'm telling you there is something called inertia of motion also. What is inertia of motion? An object which is already moving, how difficult it is to change its state of motion. That is called inertia of motion. Now you consider two objects like this. Call this as A and then call this B. They are identical objects, same mass. But assume one is moving slowly, let's say 2 meters per second. The other is moving fast, let's say 10 meters per second. Which of them is easier to stop? Or which of them is easier to deviate? Anything.
So
Which is
A.
easy to disturb? A is easy to disturb, right? Easy to disturb the change, disturb the state of motion of this system. And the other one, it is hard to disturb. Now tell me which has more inertia out of these two?
So B.
B. The second one is more difficult to disturb, so it has more inertia. Both have the same mass. Let's say this was 1 kg. This was also 1 kg. But this one has more inertia of motion. Okay. So what do you think is a measure of inertia of motion? It's clearly not mass because these two objects have the same mass, but one of them is more difficult to disturb than the other. So what do you think is a measure of inertia of motion? Anyone?
Velocity, sir.
It seems like that. Okay. The one moving at 10 meters per second is more difficult to stop it. So it seems like velocity is the factor. But let us try to discuss that also. Let's take a 1 kg mass moving with 2 meters per second and a 20 kg mass moving with 2 meters per second. Vanilla, you tell me now, which is easier to disturb? Which is easier to stop?
1 kg, sir.
Correct. So now you tell me, do you think velocity is the measure of inertia of motion?
No, sir.
In this case, it looks like mass. Okay. So it's actually both of them. To measure inertia of motion, you need to consider mass as well as velocity, which are both considered in a quantity called momentum. Do any of you know the formula for momentum?
Mass into velocity.
Mass into velocity, correct. So it takes into consideration mass as well as velocity. And you can say that momentum is a measure of inertia of motion. Now, you didn't hear about weight, but you know momentum formula also. When I asked weight formula, you didn't tell. Anyway, let it be. So yes, this is the quantity that we are going to discuss in the next class, momentum. For now, let's quickly go through what we discussed. Basically, what are forces? What are the types of forces? Okay, what force tries to do to a system? And what are some of the common forces that we come across in daily life? Next class, we will talk about momentum and another quantity called impulse, okay, which is basically change in momentum. We'll do some simple calculations and then we will start discussing laws of motion, first law, second law, third law, their applications and all. See, laws of motion is a very, very important chapter. In all the chapters that you are going to study from now onwards, these ideas will be applied. Okay, of course, motion in straight line, motion in plane, those ideas also will be applicable. In motion in straight line and a plane, we talked about velocity, acceleration. We know how to tell where an object will be after some time and all. So in those questions, they give you the velocity and acceleration, and then they expect you to tell what happens to the system. Here, by looking at the forces that act on the system, you should tell what happens to that system and then do calculations also. So we are introducing another layer of toughness in questions in terms of force. Okay. So based on force, you can calculate acceleration and tell what happens to the system. That is what you'll be learning in this chapter. Okay. Fine. We'll close this session here. Next class, we'll talk about momentum, impulse, and then laws of motion and their applications. Okay. Thank you all. If you have any questions, you can ask.